Hello everybody and welcome to my tutorial about Freecad CfdOf, tutorial number 11 in English. In this tutorial, I will show you how to simulate a simple combustion with the solver reactingFoam. So first we have to look how many substance is needed. So we will simulate a reaction between methane and oxygen, and result will be CO2 and water. So this means that for the reaction we need 1 mole of methane and 2 mole of oxygen. So now we have to calculate this into volume. We take the assumption of an ideal gas, so we can use the law for an ideal gas. The law for an ideal gas is P mal V is equal to nRT. So P is the pressure, V is the volume, N is the amount of substance in mole, R is the gas constant, and T is the temperature. Under the assumption that the pressure, the constant, and the temperature are equal for methane and oxygen, we receive. So the volume must always be in a relation 2 divided by 1. And also the volume flow of oxygen and the volume flow of methane must also be in a proportion of 2 divided by 1. And we don't take oxygen, but we take air. And we assume that the air consists of 20% oxygen. And so the necessary volume for air is given by some formulas. So the first formula is that we must take a look on the proportion. We said that the proportion must be 2 divided by 1 or 0.5 divided by 0.2.1. And then we can say that the volume flow of the air is the sum of the volume flow of oxygen and the volume flow of nitrogen. And under the assumptions that we have 23% oxygen, that means that the volume flow of oxygen is 0.23 the flow of the air. And if we take this into the equation, we receive a volume flow of 2.124 cubic meter per second. So this is the simulation model we built up. It is a small model. It's built of some millimeters. On the left side, you can see a red arrow, and we simulate with an inlet speed of 0.25 meter per second. And on the right side, we simulate the inlet air, and we say that the inlet speed is 2.4 meter per second. And on the top, you can see the yellow arrow. This will become the outlet. And normally, when you take a look on other simulations, you find that the total volume will be heated up to 2000 Kelvin or something. In this simulation, I changed this, and we will have the simulation space will only have a temperature of 293 Kelvin. So this is a normal temperature, but we will use a hotspot. We will use a hotspot with a temperature of 800 Kelvin. So this will lead to the ignition of the flow. And I've made some experiments. So of course, when you use 2000 Kelvin, then the ignition starts earlier. But I found out that if you use 800 Kelvin, then the ignition starts a bit slower. And for simulation, this looks quite interesting. So let's start with Freecad. First, we switch to the part design workbench. Make a new file. Then we can go to the sketcher. We start in the XY plane and we make a polyline. So So now our polyline is finished. We make here a constraint, vertical constraint. And here we say that both lines are parallel. These both lines are parallel. Okay. We enter here an angle of 60 degrees. Okay. We want to have a distance of 5 millimeter. I picked the wrong points. Now I hope that I got the points. Yes, 5 millimeter, that's okay. Here we want to have a distance of 5 millimeter as well. And here we want to have a distance of 5 millimeters. Okay. So now we need some symmetry constraints. These points are symmetrically. So these both points are symmetrical. Have to enlarge. These both points are symmetrical. So these both points are symmetrical. Yes, here we can say that, now it works. So next point is we say that this point is on this line. So here we apply distance of 35 millimeters. Looks good. And here we need a distance of 20 millimeters. These both points are okay. They should be symmetrical. And they should have a distance of 50 millimeters. Okay. These both points are also symmetrical. And they will have a distance of 40 millimeters. And they will have a distance of 20 millimeters. Okay. This distance will be 10 millimeters. Yeah. These both points are symmetrical. And they will have a distance of 50 millimeters. So by now the whole part is more or less restricted, but we need a hole, so we will draw the hole right now. We make a midpoint and a radius. That's good. And the distance from here to then will be 2 millimeters. The distance from the midline to this point will be 5 millimeters. I will show you afterwards for what we need this circle, and the radius will be 3 millimeters. No, sorry, the diameter is 3 millimeters. Okay, now we are finished. Everything is fine. And we can close this menu and pad this up to 10 millimeters. Click on OK. And now we have the pad, we have the base for our simulation. We can switch now to the CfdOf workbench and save this file. Now we can insert an analysis container. And first we start with the constraints. So this will be the constraint for the inlet. So we say here we have an inlet, and the velocity in x direction will be 0.25 meter per second. We click on OK. That's OK. Yes, in the next step, we will rename this area. So the label here is inlet. We will rename this to fuel. I will show you afterwards why we need a renaming, or why a renaming is useful in this special case. Here we have our second inlet. We go here, say this is an inlet, and we must pay attention to the coordinates because the flow is running in negative x direction, so the velocity is minus 2.4 meter per second. That looks good. We click on OK. And we will rename this label also to air. Okay. Now we have our inlets. Now we need an outlet. This will be the outlet. Since we will have we will have something that is more or less compressible, so we should use the pressure of the atmosphere. This will be 1 E5 or 100 megapascal. That's good. And the last boundary condition is this little hole. We pick this, click on the constraints, and say this is wall, that's okay. And here we say that we have a translating wall, and we will apply a small velocity of 0.01. So we will use this boundary condition later for a thermal boundary condition. In this case, we cannot apply the thermal boundary condition here. So yeah, we make it via a translating wall. We have to rename this later, but now we click on OK. You can wall would be okay, but in this case, I will rename this to Spark. Spark is not very correct. I will tell you later why, but for this moment, that's okay. So now we have to go to the physics model. The reacting foam needs is a transient simulation, so we switch to a transient. The other settings are okay. The fluid properties, air, that's okay, but we will change them we will change them later on. So now we go to the initial conditions. For the velocity, we specify a velocity in y direction of 0.25, and for the pressure we specify a value of 1 E5. So that's okay. Now we can go to the solver, and the first thing that we do is we will change the transient write interval. We have to increase the write interval because normally this write interval would only make 10 pictures. This is not enough, so we resize this to 0.005 seconds. So that we have, I think that we have 200 pictures, and that will make a better film out of it. Again, we save the file. So we go on the pad, define a mesh. Here we don't start the measure because we need a definition that it is a two-dimensional mesh. So we click here close. We go on the mesh, click here on the mesh refinement, and here we say that we have an extrusion and we have a 2D planar mesh. We click here on this top layer of this model. That's okay. We click add, and this will be the plane for the simulation. So we click on OK. We can go again to the measure, and we want to have a base element size of 0.8 millimeters. I've tried that in advance. That's okay. We click on write mesh case, and we start the measure. So by now the meshing is complete. We can review the mesh by clicking on load surface mesh. That looks good. This is a mesh. So the density is, of course, could be a bit more dense, but for our purpose, that's enough. We can close this. We can save the file. We go on the CFD solver, save write. Now it looks fine. The question is, how can we transform this simulation into reacting foam? I will show you now. The question is how to change setup for a simulation in reacting foam. The first thing is you should have tutorial files. You can get the tutorials files from GitHub. I've presented here the address. Then you can change PimpleFoam to reacting foam in the files case or run and case system control dict. The next thing is you must exchange the case system FV schemes and case system FV solutions with the files from the tutorial. You should delete all the files in the directory case constant and copy all files from the tutorial to case constant. Then you should copy the files alpha T, CH4, CA2, H2O, N2, O2T, and Y default from the tutorial to the directory case 0. You should change the dimensions in the file P. You should change the pressure for the internal field in P to uniform 1E5. And you should adapt the patches in all fields to the patches of the model. And then you can start the simulation in Freecad CfdOf. So now let's edit the files. We click on Edit. And here you have the file allrun. We can change now. So the last command is PimpleFoam, and we exchange this by reactingFoam. Okay, that's fine. We close. Then we go to System. We go to Contradict and edit this file again. So we can delete here the the libraries because they are not needed in this case. And the application, we can change this from PimpleFoam to reactingFoam. That's okay. Now we can close. Now next thing is to change the FE schemes and the solutions. So we click on them, delete them. And now we go to the tutorial, go on systems and copy these files into this directory. Okay. We go back to tutorial. Here we go to constant and we delete these both files because they are not needed. Here we go also to tutorial on constant and copy all these files into constant. Okay. Then in the next step, we go to the directory 0. Here we have P and U. But if you take the files from the tutorial, we have much more files. So yes, we must copy all files which are not here. We have to copy them. We click on Y default, T, O2, and so on. Copy them and insert them here. Okay. So the next thing what we must do is to exchange the pressure. We click here on Edit with Notepad, and we must now change the dimensions. So here we have 1 minus 1 minus 2, and this will become the dimension of the new file. And for the internal field, we will say this is 1E5. So this is a pressure distribution at the start. And also for the inlet, we say here we have a uniform value of 1E5. That's okay. So now we can close. And now we have to open all the files. No, first we edit the file U. This is the velocity. The velocity for the fuel and for the air, they are okay. But for the spark, here we started with 0. So we say this is 0. This is just cosmetic. You could also leave the old value there. So this is okay. We can close. And now we must edit these files. We click on Y default on T. We need the pressure. I will tell you later on why. And we can edit this file. So we go to the to P, to the pressure. And here you find 2 patches which are not inside the tutorial. So we go on Spark and the default phases, and we make a copy. So we press Ctrl C, and now we can insert these patches into the other files. And here's the reason why I renamed the labels for the inlets. So because in this tutorial, fuel is a flow coming from the left side and air is coming the flow from the right side. So we don't have to rename these patches. If you have other names like inlet, outlet or something, then you have to rename. But since we renamed this already, we don't have to rename this now. Okay, we can close. We go to the methane file, enter the missing patches, and close this. We go to CO2, to carbon dioxide, edit this, save and close. We go to the water file, insert the copied patches, save them, and that's okay. Now for nitrogen, the same. That's okay. For oxygen, the same. You see, there's a lot of work to do with copying, but yeah, you do it one time and you must also concentrate. But yeah, so we go on the file ydefort and insert the patches. That's okay. We can save this and close this. And now the last patch is the temperature. And here we have to change more. So first we insert the missing patches. For the default phases, 0 gradient is okay. But for the spark, we need a different value. So we copy here the type and the value. We insert this into the spark. And yes, I told you spark, which is not quite correct, but this should be the area where the reaction starts. So I've tested a lot of temperatures. Of course, I started with 2000, but I found out if I use 800, then the combustion starts a bit slower, and this is quite more interesting. Yes, here you find that the internal field, this is normally given with 2000, but we don't want to start the combustion on the whole field. We want to start it on a single point. So we reduce this to 293 and close this file. And now we are finished. And we can leave the directory. And we click on Run and hope that it runs now. Now the simulation has finished. The simulation ran about 8 minutes. We can start ParaViews. What's quite interesting is that we have in the error of 0.1 second, we have some interesting, something is happening. We will see later on what was this. We click on ParaView. Now the first what we take a look on is of course the temperature. We go to the first step and let it run. So here you see that we at the time of 0.1 it's still again cold. This is a starting condition, but we see now that something is happening around this hall. So here we had the boundary condition of 800 degrees, and now you see that around this there's something happening, and in the next step you see what's happening. Yeah, so now the combustion starts at the time of 0.13. We have a very high temperature of 2000 Kelvin, so it would be 1700 degrees. And um, so the start was more or less something um, that is running very fast. And you see here that we have here the high temperature, and then um, one step further, it's going to the outside, and now it goes here, and yeah. So we let it run, and we see that we have here the high temperatures, and now we have a stable conditions. And so this is a very good result. We saw that the simulation was successful. We have the temperatures that we wanted to see. So in the next step, we will take a look on methane. That's quite interesting. We go to the first frame, let it run, and at the start, the methane is coming in, but it doesn't have contact to this hole. It's moving now to the hole, and in case it gets in contact with the hole, This was, I will go back. So at this time it gets in contact with the hole and that starts burning. So here on the left side we have a high concentration, but here it gets mixed with the air. So what you see is that after combustion starts, um, nearly no methane gets out. The methane is concentrated in this area. Here we have the area of the combustion, and this is a good result. Of course, the geometry of this boiler or of this burner is not ideal, but this is only for demonstration purpose. So we take a look on the air, but you can't directly look in the air. You have to take a look on the oxygen. And here you see that, oh, just a minute, was too early. The oxygen is very fast at the hot point, and um, but the oxygen, yes, after combustion starts, some oxygen gets pulled out, but most oxygen stays here, and um, it's something that this is some kind of forces, so it's turning round, and yeah. So let's take a look on the product. Let's take a look on carbon dioxide. So at the start, we don't have any carbon dioxide, so the reaction did not start. But now the reaction starts. This is at the time of zero point 0.1. And here we see that carbon dioxide is generated. And so most what's coming out is carbon dioxide, a bit mixed with the air. So the combustion is not full. So of course, as I said, the geometry of this burner can be improved, but nevertheless, it's running. And what you see in this area is also that we have a high amount of carbon dioxide. So many of the reaction is taking place in this area. So what we can see now is take a look on Q dot. This is generated heat. And this is quite interesting. At the start, of course, we don't have any generated heat because we don't have a chemical reaction. But now it starts. And at this moment, we have many heat that is generated in this area. But as we let it run further, you see that most heat is generated over this line. So this is the line of reaction. This is in this area we have a lot of generation, and here on the airflow coming in. So we have here the area where the methane and the oxygen gets mixed. I just wanted to show you something about the reaction file. That's quite interesting. We click again on Edit, and we go to the constant, and we click on the reaction file. So the case is, how can you change to other reactions? So here we have the reaction of methane. If you want to change the reaction, you have here to exchange the chemical properties. That's more or less quite easy. Here you have the chemical reaction. That's if you know the reaction, that's possible. But if you want to change, you also have to um, change the constants. So these are the constants for the Arrhenius equation. So you have to change the parameter R, and you have to change the parameter TR. So if you want to change the reaction, you have to know these parameters. Let's come to the conclusion. The chemical reaction of gaseous substances can be simulated with reacting foam. In this example, the combustion of methane with air was simulated. Reacting foam is not included in Freecad CfdOf, but the solver can be edited. Results with reacting foam can be reviewed with ParaViews. So thank you very much for your attention. and I hope to see you in the next video. Thank you very much. Bye bye.